In this video, we're going to be experimenting with parabolas in motion using calculus. We are going to be studying these examples. Dropping a ball. So we take the second derivative, of, which is acceleration, which is equal to negative g. And we know that at time equals 0, the first derivative is equal to v0 and then y equals to h0. So then we take our equation and we take the integral of both sides, and you get the first derivative equals that. And then so to solve for the constant, we know that at time equals 0, dy dt equals v0. So then you plug in 0 for t and you get c1 equals v0, and then the first derivative is equal to that. So then you do separation of variables and you integrate again, and you get y equals that. And then to solve for the constant, you know at time equals 0, y equals h0. So then you plug 0 in for the time and you get c2 equals h0. And then your position function is this, which is a parabola. So then total time t for when the ball to reach the floor when velocity equals 0, to find this, you would put total time t into the equation, and then you would solve for t, and then you'd get t equals the square root of 2h0 over g. So we take these two equations and we plug them into Excel. And then with this part right here, we can change the different variables like height and initial velocity. But for this purpose, we're going to keep initial velocity at 0. So then we take the video of the ball dropping and we put it in slow motion, and we stop it every time it crosses a line, and then we take those points, time and position, and plot them on a curve. And then we go back to Excel, and then we take those points and we make a table out of them, and then we take those points that are being in the table and we compare them to the actual graph, and we see that they line up. Throwing a ball. We start with gravity and an xy coordinate system with our ball at position x0, y0, and we're throwing it at an initial velocity of v0 at an angle theta. And then we have our xy components. So our second derivative of y is negative g, which is acceleration. And we know that at time equals 0, the first derivative equals v sine theta, and then y equals y0. And the second derivative of x equals 0, because there's no acceleration on the horizontal plane. And then at time equals 0, the first derivative is v cosine theta with x equals x0. So we take our equations and then we integrate, and then we get that as our first derivative. And then to solve for the constant, we know that at time equals 0, these are the conditions. So then we get c1 is equal to v sine theta, and then we put that in for c, and then we do separation of variables and we integrate again, and then we get y equal to this with the constant c2. And then to solve for the constant, we know at time equals 0, these are the conditions, and then c2 equals y0, which we put into the equation, and our equation turns out to be this, which is a parabola. So now we do the same thing for the x. So we take the integral, and then we know that the integral of 0 is the constant. So we get the first derivative is equal to the constant, and then to solve for that constant, we know at t equals 0, those are the conditions, so the constant equals v0 cosine theta. And then, so that's our first derivative, we do separation of variables and we integrate it again. And then we get this equation with a constant, and then to solve for this constant, at time equals 0, x equals x0, so we get the constant equals this, and then we have our x equation. So now we're going to find y as a function of x. We take our x equation and we solve for t. So we get t is equal to that, and we substitute that into the y equation. And then once that is substituted in, that is our equation, which is a parabola. So we put these equations into Excel, and then with the sliders we can move and change things like initial velocity, initial position, and initial angle. to try to get the ball to fall into the red box. So we throw the ball in this video in slow motion and freeze it at time equals 0. On the left side we see 3 frames. The middle frame is when time equals 0. The top frame is 1 frame after time equals 0. The bottom frame is 1 frame before time equals 0. We now overlay the before and after frames on top of each other. By measuring the pixels in reference to the red grid, we can measure delta y and delta x. And since they're 2 frames apart at 240 frames per second, we can now calculate delta t by dividing 2 over 240. We can now calculate the initial velocity using this equation, and the initial angle by taking the inverse tangent of delta y over delta x. We plug all of these numbers into our Excel spreadsheet, and we can see that the predicted trajectory of the ball lands the ball in the box closer to the left side of the wall. So now we play the video in slow motion and overlay the position of the ball at every 0.1 second. If we overlay the predicted curve from Excel and put it over the curve produced in the video, we see that the 2 curves match. Draining a tank. Okay, so we have our model for our tank, and then we have our area, which is A1, and then H0, and the area of this smaller section, A0. And then the changing height, or water level, is H respect to T, and then volume is equal to A1 times HT. And then from the Bernoulli equation, we know that speed is equal to this. So then we have the volume flow rate is equal to that, with our discharge coefficient being CD. And then at time equals 0, V, our volume, is equal to A1 times H0. So then we take that information, and then we have the equation for the volume flow rate. We plug in, for V, we use root 2 G HT, and then once we have that, we plug in HG, and then we do separation of variables, and then we integrate both sides, and we get 2 root V is equal to this, and then we to find the constant C1, we do at time equals 0, the volume is A1H0, so then we take that information and we plug that in, and then we get the constant C1 is equal to 2 root of A1H0. So then we plug in for V, we plug in the A1HT, and we solve for H, and then we make CD A0 over A1 equal to R, and then so once that is R, we solve for H, and then we get H equals that, so then HT is equal to this, which is our position, which is also a parabola, and then we recognize that this is equal to the initial velocity, so then we substitute that, and then we notice that this is very similar to the drop ball equation, only with different signs, and we have our R. And then for total time T for the tank to empty, we take H and we plug in big T, and then we solve for that T, and then we get this, which is very similar to the drop ball time, except for the R ratio. So we take this equation and we put it into Excel, and then the other side here you can see the tank being filled. On Excel we can change the parameters such as the discharge coefficient and all that, and you can see how the graph moves with it. We ignore the right side of the graph, however, because once the tank fills, it doesn't, or drains, it doesn't fill again. Is ready to drain, and we start with our initial height of 10 centimeters. The video is not in slow motion, we're just freeze framing every time that the height lowers 1 centimeter. Once it does, we take those points time and we plot them on the graph. So we go back to Excel and we put the height and time points into the chart. Notice how the points don't line up with the theoretical curve. This is because of the discharge coefficient, which is set up to 1 in the spreadsheet. Once we change it to 0.75, the points line up. Now let's compare the tank draining with the ball drop. Notice how the two graphs are similar, but they have different concavities. So if we slow down the ball further and reverse the time, and we flip the height, so if we overlay the graphs on top of each other, we can see that they match. To visualize this, let's take the original slow motion ball drop video. We rotate it upside down and slow it even more. Then we take our tank video, align it with the ball drop video, and when we play them together, we can see the ball is moving at the same level with the water in time.